Okay, so hello everyone. My name is Mauricio Yarzo. I'm from Chile. I'm professor at Universidad de Concepción, Campus Chillán. I'm the party director of NENRE EfD-Chile. And today I want to share with you, I want to introduce this session. This session is AI. A1, economic incentives for sustainable energy transition. So according to the agenda, we have 4 presenters. The first one is Abram. I don't see Abram so far, from Universidad of London. And the second one is Oluwasola Omoju from National Institute for Legislative and Democratic Studies of Nigeria. And the third one is Alejandra Chuftan from Universidad Austral de Chile. And finally is Adolfo Uribe from Laboratory from Energy System Analysis, Paul Cherry Institute. So I don't see Abraham, so we can start with the second one presenter. The second one presenter is Oluwasola. Oluwasola, you have 20 minutes for your presentation, and followed by 5 minutes for your discussion, and 5 minutes for general discussion, questions, and answer from the audience. And in terms of the question and answers, the attendees can put your questions and answer on the chat box. And so, Oluwasola, the floor is yours. You can share your screen.
Okay. Can you see my screen and can you hear me?
Yes, I see your screen, but not your presentation.
Oh, my presentation is on. Okay, let me stop sharing. I'll be sure. You can just give me 1 minute.
Okay, maybe you can select your screen with your presentation.
Okay, yep. Yes, I'm trying to do that now. Just give me a minute.
Oluwasola, can you hear me? I don't see Oluwasola, can you hear me? So maybe we can follow with the next presenter, Alejandra. Please.
Thank you, Mauricio.
You have 20 minutes and 5 minutes for your discussion and 5 minutes for question and answers.
Can you see my presentation?
Yes, I see your screen.
Okay, this work, the title is Multiscalar Energy Poverty, Social and Spatial Drivers of Suppressed Energy Demand in Valdivia Households. This is part of work performed with Amapola Núñez. She is also here, and she was working in her master thesis in this project. So we will have a brief introduction of the problem, the theoretical framework, the research design, the methodology, some results and conclusions. This is a work that is already finished. So we are working in the city of Valdivia, that is the capital city of the Los Rios region, that had its first environment exceeded most of the environmental quality standards regarding air pollution. Therefore, since 2017, it has an atmospheric decontamination plan, and pollution comes mainly from residential firewood combustion and in a context of excessive firewood used for heating and high vulnerability rates in the city. In winter, 60% of households could be in energy poverty under the classic conception of energy poverty regarding spending more than 10% of the income in energy. This is also the situation of most of the cities in South Central Chile with high levels of air pollution and also of energy poverty. So we define here in Chile energy poverty as the difficulty of households to satisfy their energy needs within the home and live within the household in adequate comfort conditions. This has different consequences as exposure to air pollution, for habitability of the houses, and high energy costs, and is a consequence of low income, high energy costs, and low energy efficiency levels in houses. So in previous studies, we have seen that improving energy efficiency in houses could reduce energy demand in a high percentage, and also increase thermal comfort, but it does not always reduces energy consumption, and therefore there are no significant savings. So in this study, we're studying what is called the suppressed demand to understand that is the difference between the estimated energy demand and the observed energy demand. And this is an underexplored dimension that shows underlying causes such as the role of social spatial drivers in the concentration and or the increase of energy poverty, and that studies and previous studies address economic, social, technical, cultural, and environmental gaps, such as the quality of housing and access to better technologies, among others, but always on a housing scale. So here we are changing the scale in which we are doing our analysis. Literature defines two types of drivers of energy poverty: direct and indirect. Direct drivers are located at a household scale and include access, quality, affordability, and equity in the adequate energy access. And on the other hand, indirect drivers of energy poverty act at different scales and are social spatial characteristics that do not generate energy poverty themselves, but could drive it. Previous research have studied the effects of urban, social, and environmental dimensions on energy poverty. And regarding urban dimensions, for example, the exploration has been made on how housing quality and infrastructure define energy requirement levels in housing, as well as the relationship that urban form, for example, has on the influence of building height or density on the energy efficiency of housing. In the social dimensions, they are primarily related to population conditions that cause greater vulnerability to energy poverty. So this conceptual framework allows us to understand energy poverty across multiple scales, both at the individual household level and at the territorial level, emphasizing the analysis on its drivers and on its indicators. Particularly in Chile, it is studied through indicators of access, quality, habitability, and affordability. And in this case, suppressed energy demand is the main indicator of the study and is defined as a mixed indicator that reveals two phenomena simultaneously: affordability due to under or overconsumption in energy services, and habitability due to housing energy inefficiency. So we have this question, research question, that is, how do Valdivia's social spatial drivers spatially shape household energy poverty? And the hypothesis is that suppressed energy demand is a multidimensional indicator of energy poverty in which both physical and social drivers interact. So we propose that this indicator not only behaves individually at the household level, but also at a spatial level. These are, therefore, the general objective of the study is to analyze the social spatial configuration of the relationship established between suppressed energy demand in household and drivers of energy poverty in the city of Valdivia. And the unit of analysis corresponds to 14 neighborhoods made of several census blocks. Although neighborhood boundaries are diffuse. In practice, they are defined based on the historical and construction characteristics of the household, including several census blocks and representing the minimum unit of analysis. And these 14 neighborhoods were selected in Valdivia, and we applied 180 field surveys to the households that were distributed in these neighborhoods. The independent variables are the social spatial drivers demonstrated in previous studies at both scales, for household and neighborhood scales. And at the household scale, variables were obtained from the survey, such as household income, housing area, and type of heating, among others. And at the neighborhood scale, which comprises a set of variables, we use these 3 dimensions: social, urban, and environmental, based on the 2017 population census, the housing quality index, and the thermal amplitude index. So we have 2 parts of the process. First, the statistical modeling, the statistical description of the relations between suppressed energy demand and social spatial drivers, and then the spatial analysis, where we use local estimators that depend on their geographical location, and this model shows spatial varying relations and estimates the spatial dependence and heterogeneity of the phenomenon at different scales. So we are showing some of the results we have from this part of the study. First, at a household scale, the behavior of the dependent variable, suppressed energy demand, indicates that across all households, only 6% maintain an adequate consumption to sustain healthy indoor temperatures. 38% face excessive heating expenses, placing them in a situation of energy poverty due to affordability and equity issues in energy services. And other 56% of the households experience underconsumption, meaning they lack sufficient heating services. And as shown in the graph, suppressed energy demand shows negative figures influenced not only by housing typology, but potentially other factors. In an exploratory correlation analysis of household scale variables with suppressed energy demand, 3 dimensions on a household scale explain variability in the dependent variable: heating, housing, and household income, which will be reviewed in detail in the next slides. So when we look at heating expense, we see that houses consume more energy. Suppressed energy demand is lower. 38% of households that have high heating costs also suffer from suppressed demand, either overspending on energy service or due to unhealthy temperatures inside the house. And we also see that houses that use firewood consume 67% more energy than the rest of the houses. And this is very important when we think of an energy transition, because houses that use other fuels rather than firewood have higher levels of energy poverty. Then when we look at housing area, as the area of the house increases, the suppressed energy demand also increases. A larger area of the house means a greater energy requirement for heating, and therefore a greater chance of not achieving thermal comfort. So there's a high correlation also with the year of construction. This is mainly because thermal regulations have been implemented since year 2000, but in stages. First, only insulation for the roof, and then in 2007, insulation requirements also for floors and walls. So houses built before 2000 spend more energy than houses built after the year 2007, and have a great suppressed energy demand and an excessive spending on heating and unhealthy temperatures inside the house. Household income. A negative energy demand values that represents being cold inside the house would not be explained in general by the lack of resources to access energy heating services. It may have an impact on other variables, such as spending on less polluting energy sources and the ability to pay for thermal improvements in the house, or to face the consequences of energy poverty, among other factors. And in summary, the drivers of household scale energy poverty are under or overspending, along with energy use other than firewood, old and larger houses. And mitigating these drivers primarily depends on the availability of resources for investing in energy efficiency improvements, such as increased energy service expenditure, investing in more efficient energy types, or improving housing thermal performance. So also considering the number of people living in the household, as we assume that the higher the number of habitants, the greater the exposure to energy poverty, and therefore the more vulnerable they will be. And when we look at the household, at the neighborhood scale, the distribution of the suppressed energy demand by neighborhood is very interesting because it shows inequalities among the neighborhoods. But when these values are spatially located, there is no clear pattern that can be observed, suggesting that this distribution is rather random in the census blocks. And regarding the correlation of suppressed demand with spatial variables, only the social dimension, that is the percentage of more vulnerable population, shows a more significant correlation with suppressed demand, suggesting that the temperature range and housing quality index do not have a statistical relevance in explaining suppressed demand distribution among the neighborhoods. So the results show that heating cost and housing size are the two variables that impact heating costs and housing size are the two variables that impact both at a household level, at a neighborhood level, and as we saw previously, also have a statistical impact at the neighborhood level. On the other hand, relatively significant explanatory variables in the global model, such as housing construction year and percentage of vulnerable population, do not show spatial patterns. Different case is the heating, the type of heating, which despite not being statistically significant, shows interesting spatial patterns to observe. The heating type in the house has high significance in the global model, but not in the spatial one, suggesting it only acts at the household scale. Still, it has a spatial pattern, and neighborhoods with higher socioeconomic levels, such, for example, as El Bosque and Regional. In these neighborhoods, energy demand is not explained by the heating type, meaning changing heating may not affect energy poverty levels in these households, allowing them to opt for this less polluting alternatives. And heating costs globally behave where the relationship with suppressed demand is nearly universal in all neighborhoods. Where costs are lower, energy demand tends to rise. This household variable has a spatial pattern, and its relevance is statistically significant across the territory. So it acts at both household level and at a neighborhood level. And housing size, unlike heating costs, behaves locally. Statistical significance it has in all neighborhoods. Being local means there is a spatial variability in the relationship of suppressed demand with housing size, and this means it does not affect all neighborhoods equally. Here, if we perform a multivariate analysis of the dimensions explored previously, we observe that Corvi and Regional are two neighborhoods of different socioeconomic levels with high heating costs, but still experience suppressed energy demand. These are neighborhoods built before the year 2000 with large houses and excessive energy service spending. And the reasons for this relation in Corvi are that it has more people per household than all other neighborhoods with high rates of vulnerable population. Houses are very large and, as previously reviewed, maintain healthy indoor temperatures. In such cases, becomes a priority. The maintaining healthy indoor temperatures becomes a priority despite the low incomes. So, in contrast, Regional has different reasons.
Alejandra, 5 minutes left.
Yeah, have different reasons. Houses are equally large, but with a lower percentage of vulnerable population and fewer people yet they have high income, so excessive consumption is an option. And another case is Esperanza para Todos, where houses are very small and could easily achieve thermal comfort, but as we see, heating costs are very low, indicating an underexpenditure due to very low incomes. So certain configurations, such as neighborhood housing sizes, strongly determine the types of energy poverty in the house, this type of energy poverty in the houses. Yet when we observe this phenomenon more closely, there are different social drivers that increase household energy poverty. For example, Corby is a suitable scenario for which we could see a rebound effect, as it has a high high energy consumption per household. Therefore, with a thermal retrofit, indoor comfort increases, but heating costs do not decrease, as we have seen in many neighborhoods after the retrofit programs. Therefore, with thermal retrofit, that today, despite their high consumption, they are still cold. So the opposite case would be Picarte 4000 with a moderate energy consumption. So in this case, applying a retrofit measures could increase thermal comfort and maintain healthier indoor temperatures. The conclusions, the discussion is that we saw that decoupling the measures implemented by the contamination plans may not provide the expected long-term results, producing certain tensions between lowering PM emissions and reducing the energy poverty experienced in households. So our results show that in an older and larger houses, if a heater replacement subsidy is applied, it is very likely that the household would not be able to cover the amount of energy services required to heat the house, especially if it is located in an impoverished neighborhood. Given the high energy inefficiency of dwellings and the inadequate of the market, of the firewood market, for the most of the modern energy service. We have the examples of Picarte 4000 neighborhood that we just saw. And if a house has a thermal retrofit subsidy, it is very likely that thermal comfort will increase, but energy consumption will not significantly decrease, as we saw in the example of Corby neighborhood. We recommend that these measures should be implemented together so that the impacts of this change do not produce an unhealthy environment inside the house, and that the levels of energy consumption are effectively reduced, both mitigating the effects of energy poverty in households and reducing air pollution. And there are some opportunities in this with this type of information at both house and neighborhood scale. We can predict scenarios if retrofit and heating replacement programs are applied, and focus not only on houses that are in a situation of energy poverty, but also identify and prioritize neighborhoods or areas in which the different types of measures should be more appropriate. The multi-scale spatial analysis method allows the diagnosis of the social environmental problems, in which it can contribute to the decision-making on public policies regarding air pollution and climate change in cities, since it contributes to observing the degree of incidence of local factors of this phenomena that, as we saw, has different scales. And we saw also by the results we have obtained that it is a feasible method to observe social environmental problems from a spatial and multidimensional perspective, such as energy poverty with a view from a territorial dimension. Thank you very much.
Thank you very much, Alejandro, for your interesting presentation. Your discussant is Adolfo Uribe. Adolfo?
Yes, I'm here. Hello,
You have 5
everyone.
minutes, Adolfo. The floor is yours.
Yeah. Can you hear me?
Yes.
Yes.
Yes. Yeah. Hi, Alejandra. Thank you for your nice presentation. And sorry, everyone, for my delay. I'm in a that will be a conference inside another conference, so I need to move somehow. Yeah, I will give you 3 comments regarding what I read regarding the manuscript, but maybe the most relevant one is regarding the definition of this dependent variable, this how you call it, suppressed household energy demand, because I understand that you want to. So the idea of this variable is to try to identify how far households are from a comfort or for a technical comfort, we can say. But I mean, I want to also criticize this variable because I understand that it has two parts. One side, it has the technical energy demand that come from this housing typology, yeah. And on the other hand, you have the what you obtain for self-report, I guess, of from what actually they are really consuming in terms of energy, yeah. So my first question is probably these two, or comment is probably these two measures, they have each of them problems in terms of getting this demand. So then when you add them or subtract them, maybe you are adding these problems too. Yeah, so for example, for the first side, when you estimate, when you have the energy demand from the typology, yeah, so my idea is why you don't create from this variable another proxy, another variable that considers social characteristics like family size or other social factors that we know that are also relevant for energy demand. So I'm totally agree that the typology is a key variable. So I like it, but I criticize the fact that this size of the variable, or this element, this first element, only considers technical aspects. Yeah, so since also we understand that it's a social the energy demand is social, it's not only technical. So yeah, so my suggestion, if you want to test or try, is maybe improve this first part of this subtraction with social economical factors. That it's just an idea, yeah. And then for the other element that then you compare regarding the energy demand that actually they are currently spending, or what they have. Yeah, I didn't get. So you said that this information comes from this MAPA. There is another study, the MAPA thermic. Yeah. See, actually, I would like to know how open is that, because I mean, in terms of, because in the manuscript it said, I mean, it assumes that the reader knows very well that. Probably you know very well that, and your team also, but yeah, I'm curious about what is also behind that variable. Yeah, and why also I criticize this, because at the end you also are testing rebound effects, and from our research, actually, what I will present later, it seems like these rebound effects, if they exist, are not so big. So it can be that if households they have this improvement in terms of the heating system or infrastructure. Yeah, maybe they feel somehow they reach somehow the same comfort. Yeah, so that's something. Yeah, I wanted to point it out about if we can really add or subtract these two elements that can be that are not representing the same variable. Yeah. So yeah, that can be the first comment. And also I'm curious if you are creating now in this manuscript this variable, or something that has been used in the literature, because also yeah, but probably it's my lack of knowledge. I didn't see that before, but it can be that is part of another type of studies. But anyway, I think it's very interesting combining technical data with social or ex post data. That's actually what they are actually they are having. Yeah, I think that is there's a contribution indeed on that. It's very interesting. Yeah, so if I still have time, a second comment maybe I already mentioned is regarding the mapa térmico. I'm very curious about that. If you can share somehow in the manuscript in a future version, how we can access to the data, what is open, what is not open, and yeah, some insights about that. I saw it can be 3-4 years ago, one presentation of Infor when you were presenting this idea. And so I'm curious now what you have found. And yeah, in the manuscript that's another comment. In the manuscript, I'm referring now to table 5, but I think the presentation is table 3, when you show different fuels or technologies and the energy demand. And there are huge difference between firewood and other more sophisticated fuels like electricity. So I'm curious what is behind how you compute this energy consumption, because fuels are, the difference is quite high. So maybe you can explain more on that table. And finally, regarding the econometric estimation, in the manuscript you spend some words explaining the adjustment of the models, but probably I'm more interesting to know how your favorite estimation, the spatial one, improve in terms when we compare with the simple OLS. So more than the main statisticals of the model. So maybe or maybe I didn't see it. Yeah, maybe you are saying that somehow. Yeah, that's are my
Yes.
comments.
We have 2 minutes for Alejandra to reply to Adolfo, maybe.
Okay, I will reply in different order. First, about mapa térmico, because there I will explain some things that are important for the other questions. This was a platform that we developed in another project, like as you say, 3 years ago. It was an open platform. Now we're not using it because we're improving this platform in a new FONDEF project. That the results here that Amapola has on her thesis is part of the FONDEF project. That is like a second part of Mapa Térmico. And as you say, like our interest in continuing this work with this platform is to improve the models, because the software only calculates the performance of the house without the social aspects or variables. So in this project, we are trying to measure some social aspects that we can include in the model, so we can improve it. And then the first part of your question, the modeling, would be like a more complete calculation of the energy demand of the house, including these different social aspects that are very difficult to include because they are very different in each household. We have seen, like, for example, there are certain determinants as income, health of the inhabitants of the household, vulnerable population, and others that determine different patterns regarding energy consumption. So we're using these models to improve the calculation of the theoretical energy demand. In this part, we're working with the city of Osorno, and we have all this information that we're processing right now. And the second data regarding the survey, we have the survey from Mapa Térmico, that it was a very detailed survey regarding energy consumption in the household, different sources and for different uses. We have, and then we transform all that in kilowatt hours per square meter per year. So we could compare all the energy uses in the house, but it has a level of uncertainty because, as you know, we survey and and for example, firewood is bought in the informal market, so many people don't really know how much they use. So we have to like work with them in each survey and try to calculate the best way we can how much they use in a year, for example. So we can, because what we wanted to know about this suppressed energy demand, that I'm not seeing this term, used as suppressed energy demand. In other countries, they use more the rebound effect, because they have other problems related to the prices of energy and the rises in the consumption due to reducing the price, for example. But the thing that we have here is that when we improve something in the insulation or in the heating systems of the house, we see that most of this benefit goes to improve the comfort and not necessarily the expenditure. So we wanted to characterize also how this works and what are the determinants of these decisions in the household to improve comfort or improve, for example, or reduce consumption. So that's why we use this concept, the suppressed energy demand, so we can compare, because we think that when we know the difference between what this house should use to be in a comfort condition, like 18 hours a day, for example, and what they really use and what is missing to get to that comfort range, we can know, for example, how much of this benefit of the retrofit programs will be used in improving comfort, and then the other benefits will go to reducing consumption. In lower incomes, this is most important, because we see that most of what we have seen with the other project in Osorno is that most of the benefit goes to improving comfort, because they are in a previous state of energy poverty that is has households with very low indoor temperatures. So we know that both data, the modeling has some problems, because we need to include some variables regarding the consumption patterns, and not only the house and the construction typology. And the survey has certain level of uncertainty, but at least we have this difference that shows us that there's this energy poverty that we are not seeing, that may cause the difference in the results of applying the thermal improvements in the houses and the public programs, and especially in lower income groups. What is most interesting is that we are seeing that there's difficulties in this energy transition process, because houses that use fuels that are different from firewood are in a higher level of energy poverty because of the price of the firewood. So this would be interesting to design programs that are focused on specific groups and specific consumption patterns, for example. And that's why also this first exploration on changing the scale of analysis to the neighborhoods, because we also think that we should focus on more big scale programs, not house by house only, so we could really measure the differences or the, I think Mauricio is telling me that the time is
Maybe you can continue discussion with the chat. Thank you,
thank you,
Sandra, and thank you very much, Adolfo, for your interesting discussion. So we can move forward to Adolfo presentation. Yes?
Yes, why not?
Yes, you can share your screen, and you have 20 minutes for your presentation, and Alejandra is your discussant.
Yes, 1 minute. We're continuing the same topic somehow. Just 1 minute, 1 minute. Yeah, so I'm in the last slide already. Yes. So now, Yeah, sorry again for my background noise. Yeah, so this work I will present now is okay. It's like the second part of one project that we start in the middle of COVID pandemic during my PhD also. Currently, I'm not anymore in Chile, but I'm still doing research on this topic because the questions we have still interesting questions, yeah, to investigate. So in this work, we also analyze the synergies between clean stuff and better insulation. I will show you now some evidence from our study in the city of Temuco and Padre Las Casas in Chile, south of Chile. And okay, in our group, we probably you know my colleagues Carlos Chavez, Walter Gomez, Marcela Jaime, and Randy Bluestone. They are also part of this study. And also, I need to say that this study was possible with the support and with the help of the Ministry of Environment in Chile, especially Rocío Toro, Eduardo Schliff, and also this project had funding from EfD. Yeah. So as probably some of you know, in the south of Chile, we face one of the most relevant, important problems, environmental problems related to the use of biomass, especially for heating. And in this photo, I show you a typical picture of Temuco. Yeah, in the map also I show you where it's located. Temuco, we can say the south of Chile, and it also it's in the map is located Talca, because in the first part of our study, another manuscript of various paper that I have presented also in this seminar of SETI, we were focused there in Talca. So now the focus is in Temuco, and okay, I will tell you why in some minutes. So as you know, this is a very well-known problem, the thing of air pollution in urban areas in the urban areas of south of Chile. As consequence of one of the main effects is that approximately half of the population is living with this bad air, and the government knows that for a while in the last 10 or 15 years have been experimenting or giving different type of subsidies to replace these heaters. And also I should mention that our group had also at the beginning of this program also have helped the Ministry of Environment in Chile to test these programs. So it's a long path doing research in this area. Yeah, with the final idea to improve air quality and to improve the public health. Yeah, but now we also know, so from several years that another office in Chile, that is the Ministry of Housing and Urban Development, the MIMBU, is offering thermal insulation that it has started with a social focus, like a social focus program, but now it is really related to an energy dimension policy. Yeah, like in also is part of a full strategy of cleaning heating. Yeah, so in this study we want to show evidence related these two programs, these two actually two subsidies. Yeah, in Chile. So regarding the literature, evaluating both measures, yeah. We know first that it's very limited, this literature that covers both type of intervention. There are some studies in New Zealand, and they said that in general, the benefits of applying both programs are much more higher than the cost. of the implementation. Yeah, partially we know that international literature regarding clean heating and also thermal insulation. Yeah, and also we have local literature. Actually, Alejandra also mentioned here that clean heating is crucial for improving air quality. Yeah, and also it has an effect in the poorest. Yeah, regarding thermal insulation, the main benefits of thermal insulation has been shown on increasing the indoor temperature. Yeah, but also what is what's very interesting that these studies has been done. So there is only a few studies that are done ex post the intervention, and when we find these studies, they show that the energy savings are smaller than previously. They were estimated by only probably technical side, yeah, maybe more related to engineering studies, yeah. So our work really contributes to this literature that evaluating both measures. So what we did, we evaluate, as I mentioned, ex post, the interaction between these two programs, the heating programs and the thermal insulation program in Temuco, Chile, and we focus on three outcomes: the indoor air quality, the indoor temperature, and the fuel cost. Yeah, and we focus on these three outcomes also in our previous study in Talc. Yeah, so now what is new is that we have this interaction with the second program, the thermal insulation program. So regarding our methodology, we randomly selected almost 400 households from participants of the replacement program, of the heater replacement program, led by the Ministry of Environment. Yeah, and in these participants, we select households that they have different heating technology. Yeah, so households that they got the subsidy already, and households that they were applying to the subsidy to replace the heating system. And also we select households that they have we can say a low thermal insulation and high thermal insulation. Yeah, high thermal insulation means they applied, they got the subsidy from MINBU, or the household was built after 2007. That is, we assume, regarding the local legislation or local standards, these houses should have a good insulation. Yeah, and we did this study during the winter of 2021. Yeah, and we did measurements with electronic devices during 2 hours. Sorry, 2 days. 2 days in each household, and also we asked them to fill out some surveys, especially for the variable of fuel consumption, because we didn't measure that with sensors. Yeah, regarding indoor air quality and indoor temperature, we measure that continuously during 2 days. Yeah, and for fuel consumption, we got the consumption during the one data for the 2 days of experiment for each household. Yeah, so this picture you can see what is the heating technologies that we are including, and also you can already anticipate one issue of our samples that can potentially have an implication, that for households that they have heating, firewood heating technology, we have a very diverse group. So we have households that they have This, in the left side, this is a more sophisticated, we can say, heating technology where household can somehow manipulate the ventilation, yeah. But also we have households that they use the heating device also for cooking. And also we have households that they have very low technology in terms of efficiency and also safety, yeah, that we call them homemade heating devices, yeah. And this variable also, so this type of technology also is connected with the income or with social characteristic of the household, yeah. And in the right side of this slide, we have the homogeneous group that use pellet stove. That's the one that the government offered, yeah, in this program. And regarding low insulation and high insulation, we have yeah, here in this picture you can see how a similar type of typology. Maybe Alejandra can correct me if I say that that well. What happened with this type of household when they, after having the subsidy, so the material is improved, also they get some ventilation, passive ventilation, yeah. And so our group, so our full sample, so is divided in these 4 groups, yeah. But now in this slide, the focus is in the heating technology. So in this map, you can see in the red color, households that are use firewood, in blue color with households are using pellet. And the idea is to show you that we cover, yeah, and probably well the city of Temuco, where the households are located. In the center, we have more commercial offices, yeah. So also we include here, you can see in the map, if you know the location, if you know the city, the commune of Padre Las Casas. So regarding the measurements, in this slide I show you how was the setting inside. We installed this sensor of particulate matter. We measure temperature, as you said, as I said already, and also the humidity for technical reasons, because these sensors also they have problems. So we have also high humidity. Yeah, we can skip some data because what they are reading maybe is not the correct value. And also we did the same measurement outside of the house continuously in order to control later for outdoor conditions. Regarding the use of the stove, we use another type of sensor, the eye buttons. There are temperature sensors that when we identify peaks in the data, in the series of the data, then we know that the stove was in use. So in that way, we can correlate the using of the stove with the measurements of indoor conditions and also outdoor conditions. So regarding our results, now I will show you what we measure without controlling, so that is just the outcome variables. So here in this first figure, I show you the indoor air quality, the concentration of PM2.5, and we can see that. And here I show you the full group of pellet users, the full group that has insulation, and the combination of having pellet and having insulation. And you can see that for the 3 series, we have a similar pattern that we face better indoor air in the middle of the day, but at 4 or 6 when start the colder hours of the day, stoves are probably getting on in the whole city. Yeah, the indoor air quality is getting worse. Yeah, reaching also values of 80 micrograms per cubic meter. So we can also say We can add here that the value that is recommended by WHO that now the update that value is 15, I guess. Yeah, so we're very, very far from that value. And sorry, and regarding when we compare these three groups, yeah, we can see in this figure that the group that has insolation in general, so half of the sample, the ones that have insolation, they have worse indoor air quality. So that's interesting already. Regarding indoor temperature, so regarding indoor temperature, also we for these three series, for pellet, for insulation, and for the ones that have pellet and insulation, they present the same pattern across the day. It seems like, during the evenings when the stove are on, they get this minimum 20 degrees Celsius that we can also identify like comfort. They're all of them. But the ones that they have pellet and insulation, they have simply higher temperature. Yeah, but again, here we are just showing what we measure without controlling for other variables, even without controlling with if the stove was used or not. Yeah, so since we are interested to, okay, so I will explain you more in details in the next slide. And here in this slide, I'm showing you now for 4 groups, the cost of the fuel. Yeah, the ones that they have. So in the left side, you can, the first 2 box plots show the price. Yeah, this is the fuel cost during one day. Yeah, that is not the cost of the energy. Yeah, it's just what they said that they spent. Yeah, during one day. Since we did this exercise for 2 days, and then we divide by 2 this variable in order to get a better sense of the cost per day. Yeah, and it's not surprised that the cost of firewood is lower than the cost of pellets. Yeah, and seems like at least in the mean there is a decrease for user of firewood that has insulation. And so, yeah, and there is, okay, here we don't see a difference in the mean regarding the pellet for when we compare pellet user with only the group that has pellet and insulation, but seems like the distribution decreased, but again, we are not controlling for the use of the stove or for social characteristics. So that's why we like to do econometrics. So the first, now the table that I'm showing you is a panel data, continuous panel model for the indoor PM that we measure. And we're interested in the effect of having a pellet stove, but also using this stove. That's why we interact with the variable on. And then if we interact the same interaction, is to interact again with having an insulation program. Yeah. So here in this table, what I show you is in yellow color is the effect of having a pellet stove. In general, it shows that the indoor pollution decrease, yeah, in comparison with the household that they have firewood stuff and they use it, yeah. And this result is very robust. For this study is in terms of percentage, is in the same level as our study in talc. So that is also interesting. Yeah, that also we found there in the previous paper that the decrease was in order of 13% in the mean. And we, at least in this model, we didn't found an effect regarding the interaction of with insulation regarding this variable.
Adolfo, 5
Yes.
minutes left.
Super, thank you, Mauricio. Yeah, but now if we change the model, yeah, there is some technical details here, but if we change the model now, if we make first the interaction of having insulation and use the stove, any kind of stove the household has, and then adding the fact that the household had pellet stove. Yeah, now it seems like we identify an interesting fact here, that households that have insulation but they don't have pellet stove, the indoor pollution increase. Yeah, and the other ones that they have pellets, the effect is in the other direction. So seems like in the average, like in the model 1 and 2, we don't see this effect because we are mixing different kind of technologies. But when we split the technology and include the interaction with pellet, we can separate two groups: ones that they benefit regarding indoor pollution, and ones that they are worse. Yeah, so this is really interesting for us. I'm not gonna show results regarding these same equations for indoor temperature. We didn't find differences at all. That's our result. But regarding cost, now we don't have this panel data, continuous panel data, because with the cost of the fuel we just measure once. Yeah. So we have an sectional model. So again, when we start this exercise, first analyzing having pellet and then adding the isolation fact, yeah, having pellet increase the cost in comparison with households that they use firewood. That is what we expected, actually. And seems that when we add the insulation, yeah, we have a decrease in the cost. So it can be a synergy here. Yeah, it can be. Okay, I didn't say that, but the difference between model 1 and 2 and 3 and 4 is that we also we control using propensity score matching regarding some socioeconomical variables. Yeah. Yeah, that's our main finding. But in general, we can say that pellet stove allow decrease the indoor pollution. Yeah, that this is consistent what we found in the other city, in Talca. We will find a significant effect for regarding the variable indoor temperature when the stoves are used. Once the stoves are used, yeah, maybe I should add that, yeah, because the comparison is for that. And so that suggests limited rebound effects. So adding thermal insulation without replacing the stove could increase indoor pollution. Yeah, so it will have an implication in the policy design. And yeah, as we expected, we expected to have higher costs.
2 minutes left, Adolfo.
Thank you. But we know, so we find evidence that this increase in cost can be slightly okay, can be not so big if we add insulation. Yeah. So what now? So what is the political potential implication of this study? So okay, in a scenario, I think here we have a lot of elements of comments, or common elements with the previous presentation that Alejandra did. Yeah, I mean, in an ideal setting, yeah, the policymakers should implement both programs. Yeah, but there is a synergy between both. Yeah, regarding these two outcomes, the indoor air quality and also the cost. But that is the ideal case. But in the case of financial constraints, yeah, we suggest regarding this variable, the indoor air pollution, we should prioritize the replacement of pellets, so the heating technology. Yeah, otherwise, yeah, household can be can be worse. Yeah, and what is behind is yeah, we think that maybe a mechanism or something that explains that is probably is this homemade devices, if they have leakage of air combustion inside the house, and if we add this insulation problem, probably the air, the bad air remains for a long time there. Yeah, but I'm speculating because we're not measuring leakages or these more sophisticated variables. Yeah, so that's my presentation. Thank you.
Thank you very much, Adolfo, for your interesting presentation. So your discussant is Alejandra. Alejandra, you have 5 minutes. The floor is yours.
Thank you. Thank you, Adolfo, for your presentation. I think your work is very interesting. And it is very interesting that you assess the impact of the interactions of both programs, and especially focus on the 3 possible benefits that are temperature, reducing air pollution, and reducing household expenditure. So I'm curious about some of the results, and we'll try to make some comments on some variables that maybe are affecting some of the results and will be interesting to look at. For example, the type of firewood. Do you think that the quality and type of firewood that is different in each case can have some impact on the results that are obtained, both in terms of the pollution produced by the heating devices and the efficiency of the system? Because we have found like very big difference regarding the type of firewood and the way in which users operate the systems. Also, another question that looks like in the same way, what may be the impact of measuring pollution in neighborhoods where there are many replacement programs that have been implemented? For example, is it possible that the pollution levels of the whole neighborhood are lower in these cases and not because of a specific measure applied in that house? It's because there have been programs that are being focused on some of the neighborhoods. I know you have the map, so it's interesting to look at the spatial distribution of the program, because maybe that could also be affecting, because as we see, the patterns inside the house follow like the same patterns outside the house. So we have a great influence on the outdoor conditions, and also because the houses are not very well sealed, so we have infiltrations between indoor and outdoor conditions. Also, the reduction in indoor pollution produced in where that you can see in the cases where there is a replacement of heating devices. I think it's very interesting that you have that data, because probably this modern equipment has less pollution inside produces less indoor pollution, and also less outdoor pollution. But this is a difficult aspect to measure, because as we say, then the outdoor environment is mixed with all the houses and all the systems. So I think there's a difficult thing there to analyze because of interaction between indoor and outdoor environments. So I think that this could be difficult to measure. And also another thing that I think it's interesting to discuss that is that in this context that we are seeing of energy poverty, where we know that households live at temperatures that are way below what is recommended or what is comfortable for the activities that they have inside the house. Retrofit programs, you say that do not produce improvements in the indoor temperature. So why do you think this could be? Could it be due to some limitation in the sample or in the periods that you're measuring? For example, we always measure between 9 p.m. and 3 a.m. So we're sure that people are in the house and are using the heating device. So we can record the temperature when the house has inhabitants. Although I understand from your paper that you have a sensor that will record whether the heating is on or off, so you know when it's actually in use. But I think this may be an aspect to look at, and also that houses built after the year 2007 we know that that this is a year with the second stage of the thermal regulation, but what we have seen when we look on site at as the construction features of the house is that they usually do not comply with the regulation. What is different after the PDAs? Because after the PDAs, there has been a lot more of on-site inspection. So it's more probable that after PDA, houses really comply with the standards required in the PDAs. But after 2000 and 2007, it's probably that not so many houses comply with the standards. So there was a regulation that was on the paper, but not really applied in the house. So there's an uncertainty regarding the real state of the houses or the insulation of the houses that can also be affecting some of the conclusions. And in the same line, and the last thing is the discussion recommends that in the event of budgetary restrictions, a priority should be given to the replacement of heaters in non-insulated houses. And in this case, households would be forced to make a transition to more expensive fuels without reducing their consumption. So do you think this could increase household energy poverty? Because I am thinking that, as you said, like the best scenario is the programs working together. And what I am thinking is, I understand that you say that with insulation and not replacement of heaters, we have more indoor air pollution. That makes sense to me because the house is more sealed, and so the indoor pollution doesn't go out. But probably similar things happens when you only replace the heater without the insulation, that we have this energy poverty problem. So probably the recommendation would be always use these programs together. Like they need to work together to have the expected results and not have other negative impacts that we're not looking at. That's all the questions.
Thank you, Alejandra. And Adolfo, you have 2 minutes for a reply.
Yes, thank you for all the comments. Yeah, I will try to just say some words. I'm agreeing all of them regarding firewood. We don't know the quality of the firewood, so we don't know the humidity. Yeah, we wanted to do that. We wanted to measure humidity somehow. We discussed that with the group when we designed this exercise, the field work, but at the end we didn't measure it. But I learned this year from one study that René Reyes did in the Ministry of Energy, for the Ministry of Energy, that there is some new evidence regarding price and quality. So since we have the price, with that we can maybe make a proxy of quality. Yeah. So we can do something better with that variable. So far, yeah, our study consider that all households use the same quality, and we're not doing anything in that direction. So I'm totally agree that is a huge, but yeah, it can influence our result. Also, we don't know how they operate the system. I know that you also have done research in that line with Crystal. Yeah, no, we are not looking at that dimension. It also can have some influence in our results. Yeah, we are not doing until now any spatial analysis. So yeah, so it's nice that you pointed out. Actually, since we have the measurement of outdoor air quality across the city, only with that variable, I think we can analyze the effect of the replacement, and then if it has an influence inside. So I mean, what you suggest is perfectly feasible to analyze, I think. And yes, regarding the energy poverty, yes, so we are suggesting replace first the heating system. Yeah, but we know it has an extra cost. Yeah, but what also, but here our opinions come from looking only the indoor pollution. So also I can reply to this discussion, but what is the cost of breathing this air? What is the social cost? We also can go in that direction, if breathing a better air. What is the cost of my health for that? Yeah, but no, but in practical reason, you're right. Households, they will pay more for a better fuel, and that will be an implication in the energy poverty. Yes, and it's also thank you that you mentioned regarding the compliance or not compliance of this regulation of these standards, because we also assume that they have a good quality. So also, I mean, the households built after 2007, they are, we categorize them as good insulation, but yeah, that also can add yeah, some uncertainties on our study. So thank you for your comments again.
Thank you, Adolfo. And according to the program, we're moved forward to the next presenter. Olasola, can you hear me?
Yeah, I can hear you. Can you hear me as well?
Yes, yes.
Okay, great. Yeah, thank you for the opportunity, and apologies for the itches the last time. Okay? I think the Adolfo needs to stop sharing his screen before I can share mine.
Adolfo, please, Olasola, it's the next presenter, so he needs to share your screen.
But can you help me on that, Mauricio? I found it. Super.
Okay.
Yeah.
Okay.
Yeah, all right. Okay.
Olasola, you have 20 minutes for your presentation and 5 minutes for discussion and questions and answer for the audience.
All right, so can you see my screen now?
Yes.
Okay, so I'm presenting a paper titled Being Green and Prudent, Economy-Wide and Environmental Impacts of Renewable Energy Production Subsidy in Nigeria. So there's a paper from a project that is funded by the Partnership for Economic Policy, PEP, and this paper is already currently under consideration for publication at a journal. So I think this is the outline that I'm going to follow, and look at the motivation, the research questions, the methodology, the data, the simulation scenario, the main result, the policy implications, the conclusion and recommendation. Let me just quickly add that I think this is a macro paper. I think that the two papers that have been presented by Adolfo and Alejandro are this micro level paper. Okay, so green fiscal policies are actually becoming very important for combating climate change. And I think one of the prominent examples is the Inflation Reduction Act in the US and also the EU Green Deal. So this is government using fiscal policy in terms of like subsidy and things like that to actually address the issue of climate change. However, limited international climate financing for developing countries has necessitated the need to look inward for financing option. According to the OECD in 2022, only about 74% of climate change pledges by developed countries for developing countries were fulfilled. And however, when you look at developing countries, because of the fiscal constraints that they have, green fiscal policy raises important questions about fiscal sustainability in developing countries. So this is the focus of this study. In 2015, the Nigerian government introduced production subsidy and tax break in the National Renewable Energy and Energy Efficiency Plan. And this paper actually wants to investigate the economy-wide and environmental impacts of the subsidy, and also focus on how the subsidy itself is financed. So my research questions are these two: what are the economy-wide and environmental impacts of renewable energy production subsidy in Nigeria? And does the mode of financing the subsidy has any effect on the effectiveness and the economic impact of the subsidy? So in terms of like the methodology, I use a computable general equilibrium model computable general equilibrium model is a macro level model that are based on neoclassical economic theories, and they have been widely used to analyze the economy-wide effect of public policies, energy policies, climate change, agricultural policies, trade policy, and the rest of them. And one very importance of using a computable general equilibrium for macro level impact evaluation is that it captures the general equilibrium effect, which is basically the feedback effect that standard model do not capture, such that any change in one sector is not limited to that sector. It can also affect other sectors through change in relative prices. So for this study specifically, we use the standard PEP 11 model developed by Decaloué. So this model is a single country static model. It's just like any other CG model, like GTAP model, the AgroDep model, or any other GTAP model. I think the basic assumptions are neoclassical economic theories, but some of these theories might not be applicable to developing countries, particularly in the context of Nigeria. For example, one of the assumptions of the model is that there is full employment in the economy. However, we know that in the Nigeria economy, there is no full employment. So one of the things we did was to actually capture unemployment in the model. And basically what we did was to use the wage curve to actually vary the wages in the model so that the wages can actually vary while labor supply is fixed. So we also made some other changes to the model. In accordance to the literature, we also include electricity as a component of the value added, such that in the model, electricity is viewed as an important component of the production process. So ideally, in the standard model, where you have the labor and you have the capital. But in this model, we also include electricity as an important component of the production process. Another innovation we also included in this model was we included an environmental module just to capture the environmental effect. So basically what we did was we used the emission coefficient of different sectors and we link it with the changes in output of this sector so that we can determine when the output of this sector changes, how does the emission of this sector and the aggregate emission change. So I think this is just like a kind of like a graphical representation of the model. So basically what we are seeing here is at the top of the model, we have output, and this output is disaggregated into value added and electricity. And on the other side, we have the intermediate consumption. And the value added is actually, and based on the literature, the value added is actually disaggregated into labor, composite labor, and capital and electricity composite. And we come down that way to disaggregate the composite into capital and electricity. And we also disaggregated electricity into whether it is utility generated electricity or self-generated electricity. And the reason why this is actually very important in the context of Nigeria is the fact that only about 55% of electricity is generated by the utility. So you find out that at the household level, because the electricity supply is irregular, so almost all the households have generators where they put fuel and they generate electricity by themselves. So it's very important to capture this in the model. And the last equation here is actually showing the emission, the connection of the output of the sectors to the environmental, to the emission level. So in terms of like the data used in a standard CG model is the social accounting matrix. And the social accounting matrix shows the relationship between different sectors of the economy, as well as the link with economic agents. I think just a standard circular flow of income in standard economics. However, the latest social accounting matrix for Nigeria was published in 2010 based on 2006 economic data, right? And this social accounting matrix has 61 sectors and 62 commodities. However, between 2006 and now, when this data was developed, I think a lot of changes has happened in the Nigeria economy. So basically, we use recent data. I think we used 2016 national economy. As at the time we did this project, so we used 2000. We updated the social accounting matrix with 2016 economic data, and we used the cross entropy method that was developed by Lemelin et al. So I think we have an updated social accounting matrix at least up to 2016. So the updated data, the updated social accounting matrix has 27 sectors and 28 commodities. We also use some elasticity parameters, which were obtained from the literature. I think currently we are building a new social accounting matrix, at least for 2019 before COVID. And we are doing that with technical support from the Joint Research Center of the European Commission. Now, for this analysis, as I said, the objective is actually to look at the economic and environmental effects of this subsidy. Now, we're looking at two scenarios. So the first scenario is basically that the subsidy is absorbed by the budget in such a way that, okay, government gives subsidy for renewable energy, and this leads to deficits, like government can borrow to actually finance this deficit. Then the second one, because developing countries or governments of Nigeria or maybe other developing countries, they are also fiscally constrained. They don't have too much money for the budget. So another option is for the government to reduce spending in some sectors to accommodate the subsidy. So those are the two scenarios we look at in this simulation. So in terms of like the results, we found out that the subsidy, regardless of whether it is financed through public deficit or whether through reprioritization of government spending, it will reduce renewable energy price by about 12%. And as a result, the usage or the adoption of renewable energy will increase in all the sectors, because we can see the effect of renewable energy in all the different sectors. So the use of renewable energy in all these different sectors will increase. However, because the basic idea of energy transition is when you are increasing the use of renewable energy, you are supposed to reduce the use of fossil fuel. However, we found that although the adoption of renewable energy is increasing, but also at the same time, the use of fossil fuel is also increasing, at least marginally in some sector. So this gives us some idea that subsidy can actually increase the use of renewable energy, but it might not actually substitute fossil fuel in all sectors. So in terms of like the aggregate effect, I just selected some macroeconomic indicators: total government income, unemployment, real GDP, consumer price index. And basically what we found out under scenario A, as I said, scenario A is that the government actually financed the subsidy through public deficit, while scenario B is that government financed the subsidy through reprioritization or the readjustment of government spending. So what we found in our result is that in terms of like the economic effect is better under scenario A. And why is that? You can see that government income, or which is government revenue, only reduced by a small amount, which is 0.71%, while under scenario B, government revenue actually increased by 5.65%. Also under scenario A, unemployment reduces by unemployment rate reduces by 2.8%, while under scenario B, unemployment increased by 10%. Now, in terms of like economic output, real GDP under scenario A, real GDP increased by 0.13%, while under scenario B, it reduced by 0.61%. However, when we look at the environmental effects, looking at the emission, so we can see that the scenario B has a larger environmental effect. We can see that emission reduced by 7.4%, while under scenario A, emission reduces by only 4.12%. And basically, the basic conclusion from that is that while scenario A is better in terms of like economic indicator, in terms of like economic impact, scenario B is worse in terms of economic impact, but it's better in terms of environmental impact. It's able to actually reduce emission by a larger proportion. So what is the policy implication from this? we found out that production tax or production subsidy can be very effective in promoting renewable energy use in Nigeria. However, they might have some mixed effects on macroeconomic variables of interest, depending on how the subsidy is financed, whether it is financed by public deficit or whether it is financed by reprioritization of government spending. So when the subsidy is absorbed by the reprioritization of government spending, it has a negative effect on GDP and household welfare, but it has a larger effect on emission reduction. On the other hand, if the subsidy is absorbed via public deficit, it will increase GDP marginally.
You have 2 minutes left.
Okay, I'll finish now. So it will increase GDP marginally and household welfare will increase, but the effect on emission will be very small, at least compared to the other scenario. So the basic lesson from this finding is that the policy incentive is a no win-win situation and require tough decisions for policymakers on their priority of interest. So in terms of like conclusion and recommendation, renewable energy subsidy is effective in promoting renewable energy use, but it is not sufficient to substitute fossil fuel. The economic-wide effect depends on how the subsidy is financed. So the mixed effect of climate policy in general and renewable energy policy in particular on key macroeconomic variables should be taken into consideration when designing climate change policies. So optimal level of financing should be determined to ensure that there's a balance between the economic effects of climate change policies and their environmental effects. So I think on this note, I want to stop here. I look forward to your questions, for your comments and your suggestions. Thank you.
Thank you very much, Oluwasola, for your interesting presentation. So I don't see your discussion, but we can use the time to question and answer from the audience and comments.
Okay.
So, we have the comment on the chat, from Luis Fernandez. Is this a static general equilibrium model?
Yes, it is. It's a static general equilibrium model.
My question, if it's okay for me to answer to ask it online, my question is because some of the considerations that you could have in a dynamic model, especially on how are you going to repay the debts, could be changing some of your results. So the government spending is not going to be infinite and growing. So and that consideration would be important because if in a dynamic model you will need to repay that debt. The other thing is, I mean, your result is saying that the incentives are only generating, I mean, basically energy demand in general is increasing. That's what is happening in the model, and that's why they don't substitute between fossil fuels and renewables, but they buy both, no? And that's basically what is happening.
All right, thank you for that question. So basically what we are saying is that in this case, the energy, particularly at the sectoral level, right, demand for energy is increasing in the renewable energy sector. Renewable energy is increasing significantly. So we are supposed to see some reduction in fossil fuel energy. So in some sectors, fossil fuel energy reduces, but in some sectors that are very, very intensive in the use of fossil fuel, we can see that even instead of fossil fuel consumption in that sector to reduce, it increases marginally.
Yeah, and the other thing is, what are the channels that a government can use to reduce their spending? I mean, here what happened, it seems that it's happening is like they're firing a lot of bureaucrats or like government officials, and with that's why you had a big spike in unemployment rate. But I mean, what other possibilities could they have in rebalancing their budget in this model?
All right, yeah, thank you very much. I think another idea that we consider, because of course, one way for the government to go is actually to reprioritize the spending. But I think maybe probably within the context of the political economy of the country, we know that that might not be a popular decision, kind of. So another idea we are actually trying to also simulate in addition to this scenario is probably maybe government increasing some kind of like tax, maybe VAT on some commodities, or maybe government imposing some carbon tax on fossil fuel industry. I think these are some kind of ideas that we can simulate in addition to this. Maybe that can generate some financing for the government to actually to pay for the subsidy. Thank you. But I think it's a very interesting idea to actually use a dynamic model. I agree with you. And I think the reason why we don't want to go with dynamic at this point is, as I said, the social accounting matrix is quite old. We just updated it using some scientific method. But now we are trying to build a new, more current social accounting matrix that will be able to do some more maybe interesting and a little bit credible analysis with.
Yeah, I mean, my concern is like partly of some of the results are based on the fact that you are increasing spending that obviously is going to increase GDP, but you are not getting any cost of that. So it's basically getting higher numbers that looks beautiful in the results, but like in long term, those are not sustainable. So that's my only concern.
Yeah, I agree with you.
Okay, great. Luis Fernandez, thank you very much for your questions. And I don't see any additional questions on the chat box. So maybe we can, Olazola, maybe you can use 2 minutes to finalize your reflection about your presentation.
All right, yeah, thank you very much for the opportunity to make this presentation. I think this is the first time I'm making presentation in the SETI workshop. So I think it's actually nice to be here and to see some of this very interesting presentation. And I thank Luis Fernandez for the comments on the paper. As I said, we're actually looking forward to doing more research on this topic using a dynamic model and probably a more recent social accounting matrix. We feel that can actually help us to get some more credible results.
We have Cristobal Ruiz Tagle.
Okay.
Cristobal.
Hello, Sola. Very interesting presentation and topic, of course. And I wanted to sort of continue or follow on the previous comment, just to suggest another venue that you may think of, whether if you want to continue as the dynamic general equilibrium model, other than just revenue or tax, that is going to be, of course, unsustainable financially. You may also want to explore whether there could be positive economic spillovers, in the sense that if green technologies augment and create more economic activity, that's going to create more activity in its own. It's going to be, if that activity pays taxes, it's going to add to the tax revenue of the government. So looking at the possible added economic activity in a dynamic setting would be another channel to consider as well. And in addition to the ones that were mentioned earlier.
All right, yeah, thank you, Cristobal. Yeah, I think we will take that into consideration in further revision of this work. Thank you.
And thank you, Cristobal, and thank you, Olazola, for interesting discussion. So regarding to the program, I will say thank you very much for your attentive session. I would like to extend an invitation to all of you for attend to the tomorrow. Tomorrow we have 3 exciting sessions lined up, focus on the access to clean energy fields, as well as sustainable energy transition in Africa and green energy policies in Global South. And additionally, we will have our traditional flash talk sessions, and where you can hear brief and engaging presentation on various topics. We look forward to your participation in these sessions tomorrow. And thank you for being part of this workshop. And we will hope to see you there. Thank you very much.
Thank you, everyone. Thank you.
Bye-bye.